Welcome to Tunes Day Night. I'm your host, MC Tune, and this is pre-recorded. Normally I do a live debate right now. This is a pre-recorded debate. It's something I did on a podcast, Juan Diaz's podcast a little bit ago. I debated Chad Thompson. Now, first Chad wanted to interview me. So we had a little chat, a little interview, and then we went into the debate. The whole thing's about 2 hours long. I am at the moment somewhere on vacation, parts unknown. So enjoy this instead of a live debate tonight. I will be back next week with another live debate, hopefully with another flat earther.
Hello, everybody. This is Juan Collado Diaz with Politico, and this is Scripted Minds on YouTube. And we're going to be talking today with MC Tune and Chad Thompson, the flat earther, and the I don't know, ball earther is what you call it, Chad. I don't know exactly what do you guys want to call yourselves there. So we're gonna have a small debate on to see if the Earth is flat or not, and they will, share their evidence and share whatever perspectives they both have. So with that, I'm gonna let you both gentlemen introduce yourselves. Pretty much, tell me a little bit about you. You don't have to go in depth if you don't want, but if you want, you're more than welcome to, and share, why do you kind of like, what is your vision on the flat Earth?
Go ahead, Mike.
All right. So, yeah, I'm MC2, and you call me Mike. I have been debating flat earthers on the internet for about 6 years. I've been on YouTube for over 5 years. And my credentials are that I successfully completed middle school. That's it.
I'm barely there. My name's Chad Thompson. I am the flat earther of the group here. Juan, you're not a flat earther. I love the jacket. Thank you very much for wearing it. I actually, I don't know if you can see it right here. I have my prized possession of my globe collection. That's a 1939 globe that glows. I collect globes. I think they're going to be worth something someday when the world wakes up and agrees that the Earth is flat. I am everyday, just an average father of average educational background. Barely made it through middle school. Had to go to a vocational school to get through high school. I found girls and partying and got distracted, but I made it through. And I had no heavy interest in science at all. And I discovered flat Earth in about 2016, and am more convinced today than ever of the flat Earth. And I hope to present some evidence later on to prove that. First, I'd like to take the opportunity to interview MC2, and I appreciate you agreeing to that. I know this is off your standard format, and I feel blessed. I have to be honest. When I say blessed, I'm not religious, by the way. I know there's an association.
Chad, like MC2 also has a globe, so I think I'm the only one who does not have a globe. I used to have a glass globe, and I have a dog and a cat, so it didn't survive too long.
You made up for it with the jacket and the shirt there. I got to be honest.
I have, I'm a member of the Planetary Society. So Bill Nye sent me a shirt, a pen, and
Nice.
a signed thank you letter pretty much saying thank you for giving me money.
And he's not joking, for the record. He's not joking. So let me ask you, MC Tune. I noticed your logo, by the way, looks a lot like Tron. Were you a big Tron fan?
Well, sort of, yes. I liked it. I liked the new movie, but it looks like Toon. I just, one day I decided to edit the R into an O, and that was it. It's, I kind of lifted it, so, someday I should maybe make a new logo that's just mine and not kind of a copy, but it's what I have for now. It's fun.
If it's working this far.
Yeah.
Now let me ask you, when did you first hear about flat Earth? Like, what did you think?
Well, I think it was, it was pretty common to be taught incorrectly that people contemporary to Columbus thought the Earth was flat. That was in the Bugs Bunny cartoons, but people did not at the time think that the Earth was flat. Columbus wasn't going off to fall off the edge of the world. Nobody thought that. So that was when I would have heard it. Then I don't have any specific memory of it other than Bugs Bunny cartoons. But the modern movement of it, I heard somewhere around 2017 or it was earlier than, it was earlier than that because I found an article by Robert Schadewald, which was probably somewhere around 2010 that I saw it, or earlier, because he was still alive at the time. And he's an atheist that used the Bible, claimed that the Bible said the Earth was flat as a way to discredit the Bible. And he used to live not too far in I'm in Minneapolis area, and he was in the northwest area of the Minneapolis St. Paul area. So
I had not heard that.
Yeah, so I had found that a while ago, but yeah, the modern on YouTube version would have been late 2017, early 2018. And of course, the first time I heard of it, I'm like, well, of course, that couldn't work. The sun could never set because, like I said, I successfully completed middle school.
Yeah. And so how many times did it have to come up before you took it serious? That like, oh my gosh, is there a movement of these people out there? Like, I imagine even at first, you probably didn't even really take it serious.
Well, I still don't take it serious, but a lot of people do. So yeah, when I first saw it, it was a video responding to flat earthers measuring the angle to the sun. It was by Slice Barkane, who's a friend of mine now. And he had people all around the globe measure the angle to the sun on a particular time, particular day. And then drew angles on flat Earth and drew angles on the globe to see which worked. And the globe worked, flat Earth didn't. Pretty conclusive. Yet, flat Earthers still persist. So.
And so, when did you decide to like fight flat Earth? Like, how long? Like, was this an immediate? Like, your brave?
It was. Yeah, I started watching a few of the videos and some of the debates, and some of the flat Earth content. I got on to some online forums to discuss it with people because, when I had an interest in some particular topic, I'd go find a forum of people that were discussing it and go discuss it with them. So that's what I did. And I did that for quite a while before I even commented on any YouTube videos. And then in October of 2018, somebody, a flat earther, had issued a $100,000 challenge to show how flight charts could do basically 3 90-degree turns and come back to where you started. I'm like, well, that's easy. So I did it. First, I did it on an online flight charting system. He said he meant paper charts. So I did it on paper charts, and they're on my wall right here. Still, these are over 5 years old on my wall. So I printed out some paper charts, some real charts used by pilots. They're printed. They're not as large as real charts. They're all scaled to the same size, and drew the route on it, taped them together, and they would not fit together on the floor. I had to construct a PVC globe out of it. Each of the arms of the PVC was 5 feet long, so it was a pretty good size. It was just half a dome, half a globe, in the kitchen. Put it on there, taped it together, and it fit. So
what the heck did your wife think at this time when you were building a 5-foot globe in the kitchen?
It was another in a series of weird things that I had done. I've had a number of strange hobbies that
like what?
She is. Well, I've always been into computers. Since she met me and since I was in middle school, I've been writing software for fun and for profit, since I finished college. I did martial arts for a while. I did woodworking for a while. I don't know. Those aren't that weird. Some of the things.
Yeah, I was going to say that seems very tame. Building
yeah. Okay. Well, I built a giant trebuchet with friends of mine. We launched bowling balls 1,000 feet.
Oh, nice.
We know produce. We don't do pumpkins or anything like that. But we've done bicycles and washing machines and toilets. And running lawnmowers are my favorite. If you have to have a 2-stroke lawnmower, those are the best. So they keep running. Step one, you defeat the safety mechanism. Anytime you defeat the safety mechanism, you're gonna have fun. So you defeat that, and then you wrap it so that it's at full throttle the whole time, even when you're not touching it, and then you launch it and it's in the air, running like crazy, and then it hits the ground, instant stop. Silence overtakes everything. It's a beautiful thing.
Oh, that sounds awesome. I love underground science. I know you might not consider that underground science, but in a way it really is. And
yeah, we were going to be featured on Discovery Channel Canada, Discovery Channel Canada, until we launched a grill and it landed where the host was standing. We got her out of the way, but it landed where the host was standing, and the production guys were like, you know what? We're going to go.
Yeah. Yeah. So, I mean, speaking of you do this a lot. I mean, what do your family and friends think of your online fame, so to speak?
They know about it generally. And I try not to bring it up because there's no end to the conversation if it comes up. So I don't volunteer it to a lot of people, but a lot of people know. Everybody I works with.
I bet you're the talk of town at work. Yeah.
Well, no. But today my boss is like, hey, I saw that you hit 20,000 subscribers on your smaller channel. I'm like, yep, 70,000 on the bigger channel. So he had noticed that, and I was like, I didn't know how much he watches. He would pop into live streams every once in a while, but yeah.
That's got to be a bit weird at meetings.
I don't know. It sounds amazing to have a boss who's like that supportive. Like, gee,
yeah.
I don't know. Like, can I work where you work at? Because I mean, I don't talk about my online stuff to pretty much like any of my coworkers because I don't need my coworkers looking and then coming at work and talking about my online political and like I'm talking to Flat Earther and to chat and kind of stuff. So
yeah. Now, gotta tell you, you seem very intelligent, MC Toon. Have you ever had your IQ tested?
Only the Facebook one that fakes everybody out into thinking that they have a super high IQ. So no,
you're at 174.
I right away I'm like there's 10 questions. It took me, there's no way it's going to give me a good and then right away it goes into here's the sales offer. I'm like, oh, that was just the lost lead.
Yeah. But I mean, have you always felt smart growing up in school? Were you an advanced student?
I like you at times I screwed around. And I could have certainly applied myself more, but my friends were my friends were the ones that were in the advanced classes.
Okay.
One, a good friend of mine was valedictorian, sat next to her in physics class in senior year. And I was nowhere near her.
Wait a minute. You have a big advantage over me. You had a senior class physics class. I had no such advantage.
Well, I don't know how it is in different states. I think it's generally like this, though, is that senior year that the science is optional.
Yeah.
That's the case in Minnesota. So I
But you
opted
took
to
it.
do it.
But
Yes.
you took it. I mean, were you
Yeah.
were you into science?
Oh, yeah. Yeah. Let's see. I still have my notes from that class. Here it is. So we could take notes, and we could bring a 3x5 card to the test. We could have a cheat sheet. So I would take my notes on the 3x5 cards, right?
Now, do you have a good memory? Are you like a photographic memory?
Sometimes if I read something on a book, I know what portion of the page it was on, but I don't know. I wouldn't say that. Anyway, so these were my actual notes from high school physics class. And some of these are from college.
I was
too.
also allowed to do it. I also have like the little case.
There you go. Yeah.
Full of my notes too from physics class and like chemistry and all those.
Perfect.
I kept them just for fun.
So and the valedictorian sitting right next to me, the whole class, she'd just pound the notes out. She's filling her notebook with notes as through the lecture. And then the night before the test, she went through all of them in the tiniest handwriting possible. She crammed everything onto the note card. Right. So she took notes on that. I took notes on this, and we both did fine in the tests. So different people study different ways. So that's what she did. That's what I did.
What was your grade?
In physics.
Did you get it? Yeah.
Yeah.
Did you get it? Did you get an A?
So right away at the beginning of class, the teacher hands out the syllabus. He says, this portion of your grade is the test. This portion of your grade is the in-class labs, and this portion is the homework. I looked at all that. I figured it out. I said, you know what? Plus every test is going to have extra credit. So you could get 110%, 115% on a test. I said, well, if I don't do the homework and I get more than 100% on every test, I'll get an A in the class. So I did not do any of the homework. None of it. And the teacher pulled me into the hallway partway through the year. It was actually closer to the end of the year. And he's like, look at this. And he pulls out the grade book and he says, here's all your tests, 105%, 103%. And here's all your homework, blanks, not zeros, blanks. He goes, I'm like, okay, I'm going to get an A, aren't I? He's like, don't come and ask me for a recommendation for college. I'm like, oh, I already got accepted. So
Juan, did I make a mistake? Debating this guy? Did you hear that?
I know. I mean, I
figured the system out,
but it's never the good one. I never been on the good teams list. Like, gee,
he was playing the system.
Like I didn't have to do the homework. I didn't do it.
I watch a lot of debates, and you are like trying to nail Jello to the wall. I fully concede that you will not concede no matter what happens tonight, and I've accepted that. I can say that. Wow. So you were clearly a smart student, got into college. And were you always just like reading the science, articles, like the mainstream articles, or did not really until Flat Earth came about again? Or
I wasn't reading them a ton. I was investigating things. I suppose I was reading. I always have had a whole bunch of browser tabs open with things that I was looking into. So that Robert Schadewald thing I mentioned earlier.
Yeah.
I can sort of place the time on that because it was in a browser tab and I know which browser window. So I'd have a window with a bunch of tabs in it. And then I'd minimize that, bring it up and do a little bit and minimize it. So I know where and when that was, what computer that was on at work. And when I moved to a new computer in 2010, it was already there. So somewhere before 2010, I found that article and kept it.
Mm-hmm, mm-hmm.
So.
And then, so the Flat Earth I don't know what you called a re-movement earlier, was around 2015.
The
Ish?
earliest flat earther on YouTube was Mark Braun in March of 2014.
Okay.
That I know of. There's a guy called Stars Are Souls that was around at the time too, but he's gone. So Mark Braun is the only one from March of 2014 that I know of that's still around. And some people will say that Matt Boylan calls himself Math Powerland. Some will say, well, he started in 2011. He's not a real flat earther. I don't think you'll find anybody that thinks he's a real flat earther. He started it as a comedy routine. He created a character. This character used to work at NASA, but Matt Boylan never actually worked at NASA. The character only did. So
Gotcha.
I think he's actually just playing a character.
Gotcha. Is he still today?
He comes and goes.
Interesting.
Yeah, he doesn't talk to any of the other flat earthers. The other flat earthers that have talked to him in the past don't like him. They didn't get along with him. So he's a lone ranger out there, and he has very little support. He'll do videos, and there's hardly anybody watching him. So
now, is there any flat earthers that you just really like and get along with?
Yeah.
Have you ever been to the conventions or anything like that?
Yes, I went.
Really?
I went to Dallas in 2019, and they kicked me out of the lobby. So it's a good thing I didn't buy a ticket.
What happened?
I was in the lobby with another guy, a friend of mine, Team Skeptic, who doesn't do flat earth videos anymore. He's moved on to do other types of videos. But we were walking around in the lobby, just looking at, they have some merchandise tables and stuff, and we were looking at things and filming it. And then Robbie Davidson, the guy that managed it, he came up with the security guard and had the security guard remove us from the lobby. And we were told that the lobby was part of what they rented, and that this line in the carpet was not the area they rented, so we could be on that side of it. So that's where we stayed.
They just recognized you?
Team Skeptic introduced himself to Robbie Davidson and said, "I'd like to interview you later. Do you think that'd be fine?" That was it. And that was enough to get kicked out. So
now, can I reverse that question to you, Chad, if you don't mind answering? Have you been to any conventions?
No, I have not. Nope. I remember the first one I heard about was pretty early, and I wanted to go, but I didn't want to go enough to go, I guess. And I guess that's true every year and every convention since. Maybe I will, but not as of yet. Maybe I'll make that a 2024 goal.
Well, Karen B will probably do Flattoberfest again. The one that Robbie Davidson had done, he did 2017, 18, 19. And then he tried to sell it, but nobody bought it. So it just fizzled. Karen had started her Flattoberfest.
Now, where's that at?
I don't know. That was in South Carolina. And I think she did it first in 2019. But after Robbie Davidson stopped doing it, it got bigger. So 2020, 21, 22, and then last year it was in Vegas. So
ooh. Maybe that's a calling.
I thought about going, but Karen would never let me in. I don't know why. We got along, Karen and I got along really well for quite a while, and then I called in. She runs the live stream for Mark Sargent, one of the most well-known flat earthers. She runs the live stream. I called in to talk to Mark Sargent and said, "Hi, Karen." And then she hung up on me and then went crazy, absolutely crazy. I don't know why, because I looked at our history of communication on Facebook Messenger, and it was all super pleasant. I'm like, I like this video. It was really nice. This guy was saying mean crap about you. I'm with you on this. She's like, thanks. And then this. And so I don't know. She got a little angry. So no, I got nothing against her, but I don't think she would have let me in.
Well,
no, I feel like we need to get together and go to a flat earth convention, like all three of us, and see how we I don't know. We need to do something like that one day.
I'd be into it for sure. I'd be into it. Now, do you ever get recognized out? I imagine in your hometown you have to get recognized.
I have never in the wild gotten recognized. I went
Really?
to the one time, and this doesn't count. I went to a rocket launch, right? And if I'm going to go to a rocket launch, who's there? People that are in this, right? So I saw at the rocket launch, I'm walking along and I heard a voice. It was Red's Rhetoric. I don't know if you know who Red's Rhetoric is, but I don't know a lot of people. He's been around longer than I was. When I said I listened to debates early in 2018, he was one of the people I listened to do debates. So I recognized his voice, and so there he was. I met him along with Astronomy Live, another guy who also does. He's a PhD. He does astronomy stuff as a hobby. So I recognized them, and then the rocket didn't launch. So they scrubbed it. We all had to go home. And I'm like, well, the next day I go to my wife. I'm like, should we go to the rocket launch? She's like, let's go. So we went again. They weren't there. I knew they weren't going to be there. So then somebody else was there, Astro Rex, that I didn't recognize, but he was one of the people in the crowd, the videos, live chats and stuff. But he knew Reds and Astronomy Live. So I'm like, that doesn't count. I was at a rocket launch. I was at a, special thing. So
the rocket went off?
Yes, it did. It was pretty cool. You can feel the sonic booms in your chest when it comes down.
Wow.
And you saw it land, and when it landed, you could see the top of it because the bottom of it was obstructed by something. Who knows what could be blocking the bottom of it?
I think I know.
Mm-hmm. Actually, to be fair, there's trees in the way, so it's
That's
not a
probably
great.
what it was.
It's not a great view. Reds has gotten views because Reds has gone to a lot of the rocket launches. He's got landings where you see it and it's obstructed by water. So the curve of the water is what's obstructing the bottom of the rocket.
Yeah. Well, that is, really, I just wanted to take an opportunity and just ask you some questions. You've always really fascinated me. I never would have thought I would debate. I never thought I would debate anybody, to be honest. I really agreed to the debate to get the interview, and I imagine you probably agreed to the interview because you wanted to debate. But
it's all good.
Yeah, but no, I appreciate you going along and being a sport. Juan, did you have any questions of either of us?
Yes, I did want to ask just a couple questions that I had, and I believe that in our podcast episode of Politico, I asked Chad quite close to the same questions. So
what was that you asked?
I had two questions that I was going to ask. I think I asked closer to these questions in the podcast that we did together. So first one, and this is for both of you, whoever wants to answer first. Do you think eclipses prove that the Earth is flat, or do they prove that the Earth is round, and why?
So I'll go first. I don't think it proves either way, honestly. I think you could have explanations from both camps that would explain it. So, there's really no saying from eclipses alone, in my opinion.
Well, I think that eclipses absolutely, completely, totally can only work on the globe. And that's because of, in part, this book here, which is an eclipse, a catalog of eclipses for 10 years. These catalogs have been published for many more decades into the future than just until 2030. And they're accurate. And so being accurate on an eclipse requires it completely mandatory that you know where the Earth is, where the sun is, where the moon is, how big the Earth is, how big the moon is, and how big the sun is, where they will be in the future in relation to each other. because they don't just say it's going to happen on this day. Flat earthers like to say that sorrow cycles predict eclipses. They get the day approximately. They like to say the Antikythera mechanism does it. Not much better than sorrow cycles, or that the astronomical clock in Prague does it, which it doesn't do it any better than sorrow cycles. But here's how precise it is. This is the eclipse coming up in April 8th of 2024. It shows the exact path that the eclipse will be on, and it shows, so where you'll see the line of totality. That's the thick line, and then the exact center of the line is the best place to see it. It tells you to the second when each of the four contact points will be, when first the moon starts to touch the edge of the sun, when the moon completely eclipses the sun, when the moon stops completely eclipsing the sun, and when the moon stops eclipsing the sun at all. Those 4 points on a total solar eclipse, which is what is coming up. Those 4 points happen on an annular eclipse, which is what happened in October, which is right here. This eclipse was predicted in this book. This book was printed before 2021, yet the 2023 eclipse was perfectly predicted by it. And whether or not it was an annular eclipse, where you see the ring of fire around the moon, or a total eclipse, where it completely blocks it, those super important. You need to know how big the moon is and how far away the moon is in order to predict those things. So that leaves exactly zero wiggle room for the Earth to be any shape other than a sphere.
Now, thank you both for answering. With that, let me ask you, and this was more for Chad than MC, and we'll go around, like, you guys both can answer too. So if the Earth is flat, do you think then the moon, the sun, and every other planet in the solar system and outside of the solar system is flat, or is it just the Earth that is flat?
So I really can't say, but I can tell you this. We only see one side of the moon, and we only see one side of the sun.
If I could answer that neither of those are true. We see about 59% of the moon. There's what's called lunar libration. It does a small wobble back and forth. So we can see around the edges of it at different times. Of course, probes have been around the moon. In 1958, the crew of Apollo 8 saw it with their own eyes and got a picture of it on photographic film, which is stored in a museum in Houston, Texas, if somebody wants to go see it. It's a photographic positive, photographic slide, not a negative, just to be clear. And all of the slides have been scanned on super high resolution scanners, and you can see all of them housed by the Arizona State University has the website, one of the many that houses all 15-some thousand photographs. So we can see the backside of the moon. People have been there.
No, we can't. No, we actually can't. Now, you mentioned photographic evidence. I can show you government photographic evidence of President Kennedy being shot from the front. So, I mean, I don't trust that as a source, but I think it's pretty. Listen, I know that really my audience is the audience. We only see one side. You can say that it changes but we only see one side of the moon, and that's just the way it is. It's the same with the sun. So is it flat? I mean, I can't really say, but certainly if you look at the evidence just logically, I don't really know.
I can finish on the sun. The sun does rotate. You can use the solar filter on a camera, even a P1000 with the solar filter. You can see the sunspots on the sun. In fact, you can see sunspots go off the edge of the sun on one side and then come back days later on the other side of the sun, the same sunspots. In fact, this is so cool. There's a lunar lander a Mars lander on Mars. Every day it takes a couple pictures of the sun to get the amount of dust in the air. And on those pictures, you can see sunspots. But because of where Mars is right now, they are offset from where the Earth is in the orbit around the sun. So you can see the sunspots from the Mars rover before you can see them on Earth. with the camera. So just a couple days ago, I was asking a friend of mine that does solar photography if he could have a look at those, and we're gonna get some. There's some examples that I have, but we're gonna try to get some where I will announce ahead of time there will be a sunspot coming up in the next couple days, and it's gonna happen about this. Gonna be about this big. So
Interesting. I look forward to seeing that.
Pretty cool. So I have two more questions and then we're completely done. I said a couple, I apologize. Then you guys can go into. So this one, I love to hear all the time. Was the moon landing fake? Yes or no? And can you prove it to me?
Great question.
Oh, I'll answer then. It happened. It really did happen. There are about 15,000 photographs. So, and nobody has ever looked at those photographs, done a forensic analysis of those photographs and said, here's how the fakery was done. They've never done, I've never actually seen anybody actually look at the photographs for real. They've tried to pull up like highly compressed JPEGs from the website, not the originals, and try to analyze those. Like, that's amateur hour there. You can get the full high-res TIFF files, uncompressed TIFF files. They're very large. You can analyze them. Nobody has. There are third-party confirmations of it. The LRO is run by Arizona State University. That's the it's an orbiting satellite around the moon, and they're taking photographs. So on their website, you can see photographs of the landing sites, and you can see the debris left behind. When India went there last year with the Chanda something 2, they got pictures of the lunar landing sites, Apollo 11 and 12. And so there's independent confirmation from a different agency. United States and India don't share information on anything. I have a friend that works for ISRO in India. He's kind of frustrated because NASA won't help them at all on how to land on the moon. So there's
I seen the
additional.
India moon landing recently. Didn't they land on the moon recently?
They did, yes.
Yeah, it was. Did you see that one? The little lander coming down on the moon?
I have not. I have to probably, after this, I'm going to definitely like look that up.
Yeah, check it out.
Just for the audience's sake, flat earthers often mistake things that are labeled as artist rendering as the space agency claiming it's real. So India had an animation showing from the side of the where the lander was in relation to the surface, and a lot of flat earthers thought that India was claiming that was an actual video feed, and they never claimed it was an actual video feed.
Is there a video feed?
Of course not. There isn't a second lander landing next to the first lander doing video of it.
Yeah, they got technology to get to the moon. I'm sure they could work that out.
Maybe you should apply to work for them.
Maybe.
So, Chad, do you have a response for me for that one? What do you think?
Oh, no, I do not believe the moon landing happened. When you look at just the political climate of the Cold War, U.S. versus Russia, and then Kennedy, proclaimed that we're going to be in the moon by the end of the decade, and then 6 months before the end of the decade, there was the moon landing, quote unquote. And listen, I'm not going to get into the specifics. To be honest, I'm no expert, but just from what I've seen, I've come to completely believe that it was done for political reasons.
Okay, so and the last question, I'm gonna say this depends on how I'm gonna like you after this question. So MC2, I already like you because you have a Batman shirt, and I'm a huge Batman fan. And Chad, I like you because you're Chad. So, but this question can end that. Is Pluto is Pluto a planet? Yes or no?
It doesn't fit the definition, and I don't like that. I wish that Pluto could be a planet, but when they looked at the reasons why, I can't put together an argument to disagree with it, because Pluto, the reason why Pluto isn't defined as a planet anymore is because it hasn't cleared its orbit. Number one. Number two is that it's smaller than other things that are not planets. So if Pluto's a planet, then just because of its size, then these other things would have to be planets, and there'd just be this proliferation of planets. So they were like, well, where do we draw the line? And they said, well, if we draw the line here, then Pluto isn't a planet anymore. So by that rule, that rule it isn't.
Based on size.
In my heart, no, it's based on whether it's cleared its orbit. There's a bunch of debris in Pluto's orbit that it hasn't cleared out. It's smaller than our moon. So it's not that big, right? If it's smaller than our moon isn't a planet, is Pluto smaller than the moon? It's not a planet then, but in my heart,
let me ask you this.
In my heart, it's a planet.
Does Pluto have a fixed position every night, or does it change in relation to other fixed stars?
It moves in relation to them.
Yeah, I would say it's not a planet then.
But you can't see it in with your bare eyes. You need a pretty good telescope to see it.
I will follow the science way, but I do think it's a planet. I'm gonna say that.
In your heart, right?
In my heart is a planet, but you guys have told me here that size matter somehow. So
hey, that's science telling you that.
Science is telling me that. But if you look in my background, that orange book over here, it is I'm a huge fan of collecting things that are historically now proved wrong and accurate. And I have one that says Pluto's a planet, and next to it I have one that still I went to high school with this book and still said that Russia is a Soviet Union, and this was in 2018 before I graduated. So yeah,
2018, that's out of date.
Yes, it's very out of date, but I went to a high school that had the Soviet Union there, so I don't know. Communism is still spreading around. So I'm gonna let you guys pretty much present your debates now. We will gonna have two parts of this debate. The first one, I would like you both introduce what debate and evidence you have. Chad, do you want to start, or MC Tune? I don't know which one wants to start.
I think Chad, said you wanted to start, right? That's fine.
I don't think I did, but I certainly will.
I'm okay either way. I've done it.
Yeah, same here.
Hundreds of times.
So I guess let's start with, because I was kind of seeing your issue as the spherical excess issue. Mm-hmm. So we'll let you start that, and then I'll start with the Black Swan picture.
I'll do that. All right. So give me a second here. I need to get a
no, take your time.
Video.
I'm going to. Do you want me to wait to present my evidence until you're done?
No, I've got it.
Okay.
I've got it. So can I share my screen?
It should allow you to do so.
Okay. Let me see here.
Wait, are you going to go first? Or you just were asking in general?
I thought, did we get confused on who's starting first?
I think so. Who's going first?
I thought you wanted me to start first, but on spherical
I'm sorry.
excess.
So you're doing the spherical excess.
Yeah.
There was a misunderstanding. Go ahead. That's fine.
Okay. All right. There is, here is an exercise ball. You see that? All right. And so I put some strings on it. A, B, C at these different points. And then I measured the angles on each of them. You'll see in a second how I measure the angles. And I just chose arbitrary points. There's no particular spot. Oh, I don't have the measurements of it in that video. So just a second. I might have.
You really went all out.
Yeah.
I guess you're a hands-on kind of guy.
I taped string to a ball. It was amazing.
I mean, hey, listen, you were building a 5-foot half globe in the kitchen. So.
Yeah, that was the weird one. I did it twice, actually, because the first one was I had to improve on it. So let's see. I don't think I have it handy. So I'll just tell you that.
You can round about it.
Yeah. So when you measure, when you do it like this, you look at those angles, you measure those angles with a protractor or an angulometer, as sometimes I'll say. those angles will sum to more than 180 degrees. A triangle on a flat surface will always sum to exactly 180 degrees. So if you measure angles using doing what surveyors do and measure these angles like that, you will get, and if they sum to more than 180 degrees, then you're on the exterior of a convex surface. If they sum to 180, then that area within your margin of error, and that's very important. It could be flat, and if it sums to less than that, then you could be on a hyperbolic surface, or like a saddle. It's said. So there was a survey called the Transcontinental Triangulation and the American Arc of the Parallel. It did a very wide survey across the entire United States, right along the 39th parallel. And in this book, they're very detailed in the measurements that they took. And they list, unlike some other surveys, they list all of the data that they did. Here's an example of some triangles across Missouri. And so there we see Morgan Minoma Insane Asylum. That's actually on the roof of an insane asylum is one of the points. And they're measuring the angles. So from Morgan, it measured the angles to Minoma and the insane asylum. And it was 52 degrees, 31 minutes, 52.47 seconds. So degrees, minutes, seconds is a way to measure angles. There's 60 minutes in a degree and 60 seconds in a minute, which means that there's 3,600 seconds in a degree. This was all done longhand, so this was a convenient way to do it instead of in decimal. So this particular triangle number 1 here, when you sum those together, it gets 3.76 arc seconds more than 180 degrees. So it's a bit over 180 degrees. So that is evidence that it's concave, or not concave, convex. They have the lengths here. It's 10 kilometers, 12 kilometers, 10 kilometers, and log S. So log S is the logarithm of the length and they do this to simplify some future math things. That's why they track it, because it was, again, all longhand. Some of the larger triangles in the West Coast had significantly more spherical excess, and the spherical excess is directly proportional to the area inside the triangle. And so I asked for some volunteers to type in all of the data. I'm going to try to find another triangle here, another set of triangles. And they did. They typed in all this data you're seeing just go by. They typed it all in. And then they did the vertical angles too. So here, all right, here's another triangle. Cold Springs, Snow Mountain West, Mount Helena. These are mountains, of course. 16 arc seconds of excess. Some of these have here, this one here has 59 arc seconds of excess. So it's more than almost a 1/60th of a degree, which is actually a pretty good amount. And if you look at these angles they're measuring to 2 decimal points beyond an arc second. So they're very precise measurements. Anyway, this is, I'll show you the graph of, here you go. Here's the graph of interior angles versus distance. So the distance being the area inside the triangle, basically. And you'll see on the vertical axis is the degrees of excess, and the horizontal is the distance, the linear distance around them. And you can see at the very top there, it's almost 2.5 degrees. It's 2.35 degrees of spherical excess in this triangle. And you'll notice that while these small ones are rather small and sometimes close to the margin of error, none of them are 0. None of them are negative in the final measurement. Some people have looked at the intermediate measurements without doing the corrections for errors, margin of errors, and things like that, and found that there's 3 triangles that are correction that were less than. I think it's just 3 that were less than 180, but that's an intermediate measurement that wasn't an accurate final measurement. So these are the final measurements. Anyway, that's the spherical excess. All of these triangles are greater than 180 degrees, confirming that we are on the surface of a sphere. And furthermore, because this relationship is a line here, it's rather linear. It's not some sort of an undulating, varying radius. It's on a consistent radius, at least across the United States it is. So, but when they do spherical excess in other areas, they get the same results. So there's how spherical excess informs us that the shape of the Earth is a sphere.
Chad, I don't know if you have any follow-up questions or would like to go ahead and present.
So did you understand his argument about the triangles and so forth? Did you follow what he's saying?
Yes,
I am, yes.
Okay. So my argument is this, and I'm going to show the reality of what's going on. There is no measured excess. Any kind of excess is coming after the fact. It's. Let me just start here. Let me. It's about to start. How about now?
I still hear you.
Okay, perfect. Okay, so I think we're good. Can you hear me and see the screen?
Yes.
Oh, love it. All right, so right here, now this is the triangulation survey from Gauss, and I have all of them. And there is, right here, the first one is 179 degrees, and there's some minutes and some seconds. It's under 180 degrees. And what accounts for that is margin of error. There's lots of things that can create margin of error, but refraction is probably the biggest, but there's lots of things. And then you can look at the one underneath it. You see where it says 179, 559, 5959,
Yes.
Okay, that's an angle. And you can see there's no excess. The one underneath that, same thing, 179, there's no excess. Here is some more, 179, there's no excess. 180, now right there at number 5, you can see there is a little bit of excess. You can see it's about a second. And just so you know, a second's about 100 foot. That's what it equates out to.
Well, hold on. No, it doesn't.
No?
No. It depends on the distance. Completely depends on the distance.
Okay, that's fair. Yeah. That's fair. So what we have here is really within inside the margin of error, all of these measurements are at 180 degrees. If you look, I'm at another page. Here's more, 179, 180, 1 second of measured, observable excess. Now, if you notice next to that, they made a correction and the margin of error was only 0.12. So what's going on here is there was a note in the work. He said, we frequently fail to bring out an excess. So what is going on? Give me a second here. Right here. So what happened is all of the measured angles of that survey were within the margin of error of 180 degrees, many within a second. And so what they did is they took the longitude and latitude and they put it into a datum that used a presupposed circumference and radius to come up with the actual excess. the excess of not only this survey, but all the surveys, which I'll show, are not measured or observed, they're calculated. Every single one. There's not, all of what you showed was really just calculated. So yeah, it's going to work out perfect because there's a presupposed, so let me show you here. Just one, because I know you're not real familiar with this stuff. Let me just show you what's going on. So what is being done is there's a reference ellipsoid, which is essentially a formula that when you take and you find the latitude and longitude, it ties in to what the reference ellipsoid. So this is not measured, this is a reference. So if you look right here, for example, GPS uses this specific geodetic datum, WGS 84. You can see it says right there, it's based on a consistent set of constant and model parameters that describe the Earth's size, shape, and gravity. Right here are the presets. That's presupposing the size. And to give you a visual, this is what's going on. You can see the claim is obviously we have mountains and valleys and rivers, so the Earth's surface as a ball is not exactly level. So they use a reference ellipsoid based on the center of the Earth. And then once you have that, all you have to do is tie in to the coordinates, and it gives you what you would normally be on a ball. So let me go back here, and I'm going to go to different survey. So this is a survey that's off of your website. And this is, again, a situation where they've tied into a datum. All of the other surveys have no measured spherical axis. So here's another one. Right here. You can just look at them. All 180 or 179 to 180, all within the margin of error. Every single one. Here they talk about it. Every single survey ties in to the geodetic datum or the ellipsoid reference. There's no measured excess on anything. All of these right here, it literally tells you what they did. It says the quantity by which the sum of the three observed angles of a spherical triangle should have exceeded 180 degrees was found as follows. Because the excess of the three angles of a spherical triangle above 180 degrees, it basically gives the formula how they backdoored excess. Right there, it lays it right out. And this was, I mean,
that's, go back for a second on that.
Yeah. That right there, that's the triangulation survey of Great Britain.
Okay. That's not the formula, but go ahead.
Yeah, that's, I mean, this is right off of the survey document. And you can see here, I can go through all of these. There's no spherical excess. Now, as we have progressed forward, what surveyors do is, let me show you. Tell you what, let me just back up here. This right here, I have a friend of mine who's a cartographer. He works with surveyors, And I asked him about it, and he said that that then comes, I was asking him about surveys. He said, then comes the measured angles from the station in that row and between the two others. After a small correction is made on the arc seconds, I think this is accounting for the fact that the stations are on mountains, has different elevations with the correction done, measured angles shown as spherical angles. So there's a calculation. All of this spherical excess is all calculated. There's no measured excess. And you can go through, and when you actually look at the documents, they tell you that. This is another one, and they basically explain how they backdoor into that excess. So if you just pick any survey, I can go through and look at documentation. Right there it is, the computation of the spherical excess of the triangles. That's what's happening. So you can't really claim spherical excess when I can show right here it's measured flat consistently, all of them. So that's what I would say.
So with that, Chad, are you done presenting?
Yeah.
Okay, so MC Toon, do you have like any like follow-up arguments, any questions to Chad?
Yeah. So you didn't directly address, except for showing one screenshot, the survey that I put up.
Which one was that?
The Transcontinental Triangulation, the American Arc Parallel, published in 1900. So I can tell you, I can assure you, you cannot do the same. So when I asked you to put up that page and let me finish reading through it, you said this was the formula that they used to calculate in the excess.
That survey.
That wasn't a formula how they did it. But that really is immaterial to mine. I just want to make a note of that. So I'll look up that particular survey. I haven't looked at that one in particular. There's a lot. So
I think that's on your website. I got that from your website.
The survey from Gauss?
The principal triangulation. Gauss? No, not that one. The principal triangulation of Great Britain from 1791.
Oh, that's from Airy. Is that from
No,
Airy?
It's not from Airy. It's from William Roy. But oddly enough, he did use Airy's zenith sector, which is the ellipsoid reference. So again, it's referencing this reference based on the center of Earth, and then you cannot come back later and claim curvature.
Which one is
It's
Roy?
presupposing.
Hold it just a sec. Which one is Roy?
William Roy. He's the principal triangulation of Great Britain. They were determining the distance from Greenwich to Paris.
I don't know if I have that on my website. I have a lot of surveys on my website. Eastern oblique arc of the U.S., Texas, California, primary, California, Washington, transcontinental triangulation, primary triangulation of 104th meridian in Colorado and Utah and Nevada. I don't have, so anyway, that's beside the point. So the one that you did bring up showed that there was almost one full arc minute of,
which one?
Of excess. That was Pilot Peak and Ibapaw. It was, I think, the second to the bottom on your file system.
Let me look. Bear with me here, because there's nothing that's even close to a minute. Let me just keep
actually
looking.
There's the largest one in that survey is 2.3 degrees.
What survey are we talking about here?
Transcontinental triangulation. That's the only one I brought up.
I don't. Yeah, I didn't look at the transcontinental triangulation.
I mean, you had a screenshot of it. Hold on. You had a screenshot from the PDF that I referenced in your folder. You showed it a little bit ago.
I might have.
Okay, so
I was showing where they used.
In a different survey you showed. So you didn't show in the one that I presented where anything didn't match, and you made claims about how they did the formulation and how the formulas were applied, but the screenshot that you had wasn't actually the formula that they were using to do any fill-ins on that to calculate in. So I have gone over all of the claims that different people have said. I've read through all of the discussion in the transcontinental triangulation, specifically starting on page 37, general discussion for local adjustments of the directional observations, and it references a book by T.W. Wright published in 1884 about how they put the residuals into this series of interlinked equations to resolve the residuals and do the corrections. That's all a zero sum game. So and if you did have on your screen there a few of the ways that they showing the corrections that they did, they tend to be zero sum as well. And what I mean by zero sum is a particular station it has measurements in multiple. It's not just one triangle, it's part of many triangles. So all the way around, there's 360 degrees. And so if that particular one was off in between two stations, between station A and B, and an angle between B and C, and the modification of the residuals determined that the one between A and B was 0.1 arc second too much. Well, they couldn't just add 0.1 arc second to that angle, because then you have 360.1 or plus 0.1 arc seconds. So all of them have to be a zero sum gain. So they say, well, if we're going to modify this one, then we have to modify another one so that we're not actually changing the full number of degrees that were measured from this particular station. So if you look at those, all of those are zero sum, at least in the triangulation that I've looked at. I didn't look at the one that you referenced. I can only respond. I should only have to respond to the one that I presented. You should have responded to the one I presented.
That in the sense that I've presented literal measured evidence of a flat Earth right here with no excess, measured observable excess.
Not actually at all, because
I can post it up again
because when you do the corrections, it shows up. But you also did make a point, and this is a really good point. These are small triangles, and the sum of the angles are still within the margin of error. So the margin of error
at 180 degrees. At 180 degrees, which means that they're it's kind of a black swan.
What's the margin of error?
Up to 4 seconds.
Okay, so if plus or minus 4 seconds, right?
Mm-hmm.
So if the measurement is off by 4 seconds, it's still within the margin of error. So it's inconclusive. It needs to be more than the margin of error to be conclusive.
But that's not what we see. We don't see any measurements beyond the margin of error. That's my point.
In the one you cited. In the one I cited, there's many. There's hundreds and hundreds in the one I cited.
Well, it's a black swan. Either the Earth was flat in 1821 and then curved,
but Chad,
or else
you said it's within the margin of error. I don't think you understand.
The ellipsoid reference to get that excess.
Do you know what the margin of error means? It means when you're under the margin of error, you can't be certain of the measurement.
No, listen.
You don't know,
but always a margin of error. You're never going to be certain.
Absolutely.
If it's within the margin of error, it's acceptable. So it's
they're
well
all
known.
No.
Yeah.
No.
Yeah.
Oh my gosh. You're backwards on that. If the margin of error is plus or minus 4, and they're within 1/10 of an arc second, then it's inconclusive. You need to be more. You need to be more than 4 arc seconds.
At 180 degrees, within the margin of error. I mean, I can show you. I can show you dozens of measurements.
Chad, you're backwards.
Literally.
Well, I have 200, more than 200.
And here's what I could do.
I put it on screen. I literally put it on screen.
Where they tied into the ellipsoid reference.
You tried, but it wasn't the actual formula. On your survey, you didn't address my survey.
So you don't trust the surveyor?
You didn't.
You think the surveyor didn't know what formula he used?
I know very well what they did, but the formula you claimed as a formula wasn't actually what you said it was.
Oh, it's not?
No.
What was it?
It wasn't giving the formula for how they were adjusting each individual angle.
That's what it said.
No.
That's exactly what it said.
No, it wasn't.
Yeah.
And as you said, all
10
of those
times.
measurements were too small. You need to have something larger. It needs to be bigger than
No, they weren't
the
all
margin
too
of
small.
error.
There was some that were a second, 0.22
But you
seconds
said-
over 180.
Yeah, but you said the
0.22
margin of error was
seconds.
4.
Margin of error is 4.
Yeah, you're on the
And
wrong side of it.
They were so good, they didn't need that margin of error.
You're on the wrong side of the margin of error.
I think I'm telling you that they measured exactly within 4 seconds, 180
right.
degrees
Well,
on
then-
every
then-
single
then
measurement.
Tell me this. For those particular triangles, I have the math on this in the spreadsheet that I referenced. It's on everybody can look at my spreadsheet, mctoon.net/SE. There's a link to the spreadsheet. Anybody can look at it. All of the data has been typed in for the transcontinental triangulation, including the ability for you to take those angles. You can take those angles and you can take the predicted spherical excess for that, and you can see what it would be predicted to be and see if it's within that margin
It's
of error
going to
or
match
not.
exactly.
So
Because it's after the presupposed tie into the ellipsoid
let me
reference.
let me finish my sentence.
I'm sorry.
here.
I'm sorry. I thought you were.
So if the triangles that you were looking at are small, not if, I know that they're very small. So if you look at the size of those triangles and you look at the predicted amount of spherical excess for a globe of a particular size, you will find that the predicted amount of spherical excess is very small. And that amount of spherical excess is less than the margin of error of the sum of the measurements. So it's inconclusive.
That's not true. And are you done? I apologize. I don't want to interrupt you.
Yeah.
Okay. So, I kind of anticipated you would say that. So what I did is I went ahead and I looked at one of your surveys that it showed a spherical reference. I looked at the size and I compared it to one that I have to compare the size to see what you would kind of expect. And in fact, I'm going to share my screen here again. So this down here, this is a survey.
Wait, that one right there. That's the one.
That I know came off your website.
Yep.
Yeah. So that one right there, you can take a look. And
39 arc seconds over 180.
Yes, 39 arc seconds over 180. Now, if you look at the distance there, you have, I think those are like around average of 80 miles.
It's all kilometers there, 137.
Yeah, no, I
kilometers.
converted it. I'm sorry. It's just so I imagine there's a lot of Americans watching. It's real close to, average of 80 miles each. Not exactly, but real close. And you can see right there's 39 seconds of excess. And then this here, this is a survey that is about 43 miles, 65 miles, 52 miles. And then the other ones I can show you are over 100 miles. And they all are right here within usually 2 seconds of 180 degrees. So
wait, where's the mileage on that one? Where's the length of the size?
What that is, I can tell you what that is.
You're looking at like 13 there, right? So triangle 13.
So yeah, number 4, all the way over number 4.
4, okay.
Yeah, that is that's the Gauss survey.
Okay. And what are the lengths of the sides?
So the lengths are, apologize here, 43 miles, 52 miles, and 65 miles.
All right.
And there's other surveys I can show you that are...
Wait. Did you convert it to miles? Because was that originally in miles? Because these older ones are typically not even in miles.
No, I converted it. I converted it.
Just
so we
toises
can all
or fathoms?
What's that?
Were they toises or fathoms?
I don't know.
Okay.
I don't know. Yeah, don't know.
Okay, 43,
but I do know as
43 miles.
It's 43, 52 miles, and 65 miles. And you can see there's no spherical excess there. None. So, I mean, that is my evidence.
But there is spherical excess, 180.
Nope. That's 179. If you can see...
We said triangle 4. Hold on. You confused me. Triangle 4 or triangle 13? Which one?
No. If you look all the way to the left, it's numbered 1, 2, 3, 4, and it's highlighted.
I see
the highlighted.
I see the highlight. It's highlighting triangle
it's
number
highlighted.
4, triangle 13, and triangle 22.
Yes. No, it's I got an arrow pointing to it. You see the red arrow?
Okay, that's triangle 13.
Okay, that is the total. Triangle 13, 12, and looks like those are the mountains. Those are the stations. Sorry about that. You were confusing me. 13, 12, and 10. Those are the stations. Okay. So you look at the red arrow. It's pointing. There's no spherical excess, and so that's as plain as day. I mean, what I mean is that's about as strong of an evidence as I can give. And I can go through all of these.
What's that 9,000? What's that 9,202? All right. Well, tell you what. I'm unfamiliar with this particular survey. I'd love to look at it. There was a number just before you left, that 9,202. I was wondering what that was. If that maybe is the internal, either the perimeter or the area of the inside in some unknown unit.
I don't know. I'd have to look into it as well.
Okay. Well, so I can't speak to that particular survey without having more time with it, but I certainly will. I
understand. That's why I wanted to produce 2, but we could go through all of them in depth at a future point if you'd like.
Yeah. Well, I like, I always go to the transcontinental triangulation because it has so much detail published in it, including all the detail on how they came up with all the numbers. So every single number in there has a description of how they got it.
Yeah.
So when they're saying they did a correction, that there's a description somewhere else in the book saying how they did that correction. Even my favorite one is the at the high elevations, they made slight adjustments to the azimuth angles. Azimuth is the horizontal angles because of the elevation. Because when you're high elevation above a sphere, the angles, depending on the direction you're looking, is slightly off. And so there's formula of 0.00006 arc seconds times the sine of the angle, something like that. It never is more than just a couple tenths of an arc second on these triangles that have excesses of 1 or 2 degrees. So it's 3,600th divided by 10 modification. So that the degree is the formula 0.000066 times sine of 2 times the angle times the height in feet of the station. So a very small adjustment.
Amazing.
So yeah, and it's because they were doing such a precise job in this particular survey that's why I like it so much, because they're very open about it, and they were super particular in their attention to detail. In fact, in a survey like that, they'll do a baseline measurement using an actual physical measurement.
Always, yeah.
So they'll start one end. Always on one end, you start with the one side of the triangle that you physically measure using a chain or Invar rods. Invar is a particular type of metal that doesn't expand or contract much. And so there's one that was in California that was the YOLO base, they call it. And I like that. I have a friend that has YOLO tattooed on his eyelids.
Yeah, do you really?
Yes. He was in prison. He had a rough life. He's since gotten out and totally changed his life around. A great guy, Jon Snow. Love him. And he's had a total life change since that. So, but yeah, he has YOLO on his eyelids. Anyway, the YOLO base, which has at the time nothing to do with the "you only live once" meme, it details a little bit, but there's additional information online that I found on the specifics of how they did that particular baseline measurement. Is really cool. But the interesting thing is they do this really precise baseline measurement, and they do all the triangulation. And they've gone hundreds of miles doing triangles point to point. No baseline measurements. They get to another baseline. They do the baseline measurement. They're off by 2 centimeters.
Yeah.
Amazing precision.
Yeah, absolutely. Even back in this survey from 1791, over 7 miles, they had less than an inch off on that base triangulation. So, or that base measurement rather. So yeah, I don't know. Juan, I don't know. Do you want to ask any questions, or you want to have maybe MC Toon go straight into his Black Swan presentation? What do you want to do?
I would say let's go into the Black Swan presentation. I think you guys have been very clear, specifically, like at least for me to understand both sides. So I would say let's go back into the next presentation, and if I have questions about that, I'll ask those questions.
All right. Well, the Black Swan is your claim, not mine. So you need to.
You want me to go first?
That's not my claim.
Okay. No, I know. It's just something I thought would be fun to go over.
Yeah.
All right. So, Juan, I'm gonna talk to you because I know you're not familiar. I told you about it, right? Let me share my screen and I'll go through this. Okay.
Are you like sharing the Black Swan photo that you shared with me once, I believe?
Yes. I'm going to share so you can kind of get an idea. I'm going to talk. Okay. I'm going to talk you through this. Can you hear and see me? Juan, yes. Can you? MC10, you got me?
Yep.
Okay, perfect. All right, so I'm going to pull up right here. Let me just see what we got. All right, so let me get to it. All right, I'm clearly an amateur here, guys. Okay, so this right here is the Black Swan photo. Now, this is 2 platforms out on the ocean off of California. Now, this is zoomed in, very highly zoomed in. You can see that left platform is further out, and that platform we know is about 9.4 miles from the observer. And essentially, there is a formula that can be utilized where the observer height for this camera was a foot off the ground. And so essentially what that does, Juan, is that makes the physical horizon 1.22 miles out. Okay? Does that make sense?
Yes.
Juan, okay. All right. I just want to make sure. I don't want this to be too complicated. So here's the platform. Now, if you change contrast, you can see the horizon. But let's call this the apparent horizon. Okay. By apparent, I mean it fluctuates with refraction, but that's where we can see it. Okay, it's out. You see how it's out past that second platform on the left? I don't know exactly, but if you say that platform's 9.4 miles, it's 10, 11 miles plus approximately. Okay. Now we should, and how far you can see on a ball is based on the observer height. How far you can see the horizon. Now, again, in this picture, it should be about 1.22 miles, 1.25 miles out. Now, we can see all the way out to 10 miles. Now, what is going on here? So what ball earthers claim is that it's refraction that is moving the geometric horizon 9 miles out and taking it past that platform. Now, what I'm claiming is that refraction actually does the complete opposite and makes it so that the horizon becomes closer to you, not further away. Okay, so let me show you what refraction does. Okay, now watch this. If you elevate up, you can see further. Now you see all that refraction or all that mirage, right? That's basically the bending of light, bringing right there. It just brought the actual. This is a flat road. Now we're very close to the ground. So what happens is the horizon, because of refraction, it looks closer to the observer. So that goes completely against. Now this right here, this is another example of refraction. So this here, it looks like a floating ship, but what's actually happening is the actual horizon, it almost disappears and goes beyond the boat. So it looks like it's floating, but the ocean disappears. Now I'm going to show you again, this here is atmospheric refraction, okay? Let me show you.
Now, Chad, if you don't mind me asking in between here, so the horizon line is supposed to be the line where the Earth ends?
Well, no, the horizon line is where the curve essentially starts on a ball, right? So if you're standing on a ball and you look down, the Earth is going to start to curve down and away from you. At 1.2 miles, that's where it starts.
No, the curve starts at your feet. The curve is everywhere.
Yeah, that's true. And then at 10 miles out, it should be about 60-something miles down. But what happens is actually this refraction is bringing the horizon closer. It's not making it further away. And here's an example. Let me show you. Let me find it. All right. The world gets to see my pictures. As my beautiful girlfriend.
No worries, I will blur that in the editing.
So here's an example of what atmospheric refraction looks like. Now you see how it's changing and it's making the ground go up and down. It's making the buildings look like they're disappearing and then coming back. You see that? That's atmospheric refraction and what kind of effect it has on objects. And you can see the building, it looks like it's gone there by curvature, but in reality, once the refraction changes, you can see more of it. So essentially, and this, by the way, this is the view of, if you zoom all the way in, you can't see those platforms. When you zoom all the way out to 10 miles, the horizon goes beyond. And again, we know there's no example that can be shown where the horizon gets further away. Like what's on the screen right now, what actually happens is it becomes closer to the observer. So the reality is that refraction is bringing that horizon even closer to us. It cannot be used as an excuse to make the horizon go from 1.22 miles out to 10, 11 miles. Let me show you another example. This is another example. And you can see, if you look at those converging lines, the horizon continues, but the refraction makes it disappear and brings that actual apparent horizon closer to us. So here's an example of what refraction does. It brings closer. See how it's bringing that closer? Here's that picture. That's a flat bridge. This is an example of what refraction does to objects. It makes objects disappear from the bottom up. So this is a boat on the left that on Monday, you can see the entire hull is obscured. And then on the right, it's the same channel, and you can see the boat, you can see the hull. The difference is refraction. That's the difference. So this right here, I'm going to go for it. This is an example of refraction I've seen online. And just so I can give you an idea, this is, it's a very crude experiment, but I just want to illustrate my point. This is a laser beam through 2 fish tanks, and there's a picture on the far side. It's a boat, and what they did is they added sugar to give a gradient of density to the water. So what happens is you see curvature of that laser. You see curvature. Now, here's what you find. That's not a very good picture. Let me show you. I can actually get a little bit better here. So you can see what happens is the actual image itself raised. You see there on the right? The red line is the baseline. So you can see refraction made that image rise. And the other thing, let me see here. If I was a professional, I'd be fired. Okay, here it is right here. So this is a close-up of the image. So although the image in general raised, it actually took the boat lower, and you can see it compresses, almost as if it looks like it's going over a curve or it's hidden by the curve. What that is refraction. Refraction changes what we see. And there are a ton of examples. So this right here, just going on what we see, I could prove to you that every road comes to a point in the distance, right? That's an optical illusion. We know that's not the case.
That's perspective, not refraction.
That's perspective. I'm just making a point that what we see is not always what we get. So I can show examples of the horizon coming closer, but never further away. And it's certainly not going to take the horizon 9 miles out. There's no other example where that can be shown. The platform we know is 9 miles. It didn't. The light didn't move the platform. So, I guess that's my argument, is that the refraction didn't make the horizon further out, it closer.
Okay, when you're done, don't close this. I want to have you bring some up. But when just before you close, don't let me stop you though. Yeah,
no, go ahead. Go ahead. I'm good.
Okay. All right. Bring up the bridge again there.
Like Pontchartrain?
No.
Pontchartrain train?
No. The bridge there.
Which bridge? Which one?
Right
this
there.
one.
Yep. That one.
Gotcha.
Yeah. That's a bridge. It's not a road. It's not right.
Yeah.
And it's also you don't know if it's flat. You haven't seen the survey of it, right?
No, I'm sure it's.
Okay.
I mean, we can look at it and see it's level.
We don't know. As your point, your point is, hold on. Your point is that what we see isn't what is necessarily the case. So we would need to actually see the survey to know whether or not that
we don't
bridge
need
is
to
curved.
see the survey to know that refraction is bringing that horizon closer to us. We can see that.
That my point is, just focus on my point. My point is, you don't know if that bridge is flat or not because you have not seen the survey. And we
the bridge
know
doesn't have to be flat.
By your own example that we cannot trust what we see to evaluate whether or not that bridge is flat or not. I just want to make that point. When you said that bridge is flat, you don't know the bridge is flat.
Okay, let me respond to that. So what I'm saying is we don't have to have a flat bridge. All we really have to see is, number one,
okay,
let me just
retract your claim then.
Excuse me?
Just retract your claim that the bridge is flat and it's done.
Okay, I don't know the exact flatness of that bridge.
Okay,
yeah, that's a true statement.
Okay,
I don't know that. But what we do know is
this my turn or not?
Excuse me?
Is it my turn or not? If you're done.
Oh, I thought I was responding to your question. You asked me a question.
Okay.
I was responding to that only.
Okay. Do you have a device that's answering you?
My Siri jumped on. Yeah, no, I was just saying that we don't always get what we see. What we have is a very long bridge, but what we actually see is a short horizon due to refraction. That's all.
All right. Alexa, play Rock Lobster by the B-52s. All right. So that bridge, let me ask you, Is that bridge hotter or colder than the air?
It's hard to say. It is both at times, both hotter or colder. It depends.
Well, it's in the sunlight, and we know about roads. We know about bridges. That bridge is hotter than the air. And we know then that another sign of that is that miraging that was happening there, right? That happens when
that's refraction, correct?
Yeah, refraction causes miraging. That's the cause of it. In a vacuum, you get no miraging, you get no superior mirage, no refraction, none of that. So that was due to some sort of refraction, and that miraging, which is that mirroring, that was very clear on there. That's because the road is quite a bit hotter. It's significantly hotter than the air, right? You walk barefoot on a blacktop road, you know it's hot. And so that was a sunny day. And so that bridge is hot, significantly hotter than the air. Now, water is colder than air. So your example isn't a good analog, because we have the reverse condition over water. So over water, the air is warmer than the water. So
not always. No, that's not always true.
True. It's not always true, but it's the general case, especially on a warm day, because the specific heat of water is one.
Are you suggesting light doesn't refract over water?
No. Are you going to interrupt me?
I apologize. I thought we were having a discussion. I'm sorry.
This is my presentation.
Oh, I'm sorry. I'm such an idiot. I'm sorry. I thought we were. I apologize.
Okay.
Go on.
Okay. Water in the base case is colder than the air, and so refraction is absolutely happens because of that. And you have a higher index of refraction near the water, and the index of refraction decreases as you gain elevation. If you have a overcast day, then you have a pretty simple stack of gradient of index of refraction. And if it's sunny, then you have a super complex one. And if it's later in the day, it can get more and more complex if it's been sunny. So downward. So what happens is light bends toward the higher index of refraction. So when light is traveling, skimming across the surface of the water, you have a higher index of refraction closer to the water. So the light is going to bend downward. So I'm going to share my screen to show a diagram of how that works, so that people have a good idea. So here's Batman looking at something there with no refraction, just a
You're talking my language now.
A straight line. Yeah, I made this years ago. I love Batman. Then when that same ray of light is refracted, you see it doesn't get to Batman. It's going to bend down and he won't see it at all. So, but because light emits in all directions from whatever you're looking at, another ray of light will get to you. The one that would otherwise have gone over Batman's head is now refracted down to get to Batman's eyes. Does that make sense, Juan?
Yes.
So we have this bending light, and this is the case over water. Is the base case, because near the surface it's cooler, higher index of refraction. This is the opposite of that road, because the road has crazy layering, and in general the road is hotter. So then that ray that does get to Batman's eyes makes it look like the object is elevated above it. And you saw that in the sugar water one. There's other sugar water ones that also show similar things to that. So that's how downward refraction causes things to appear higher. That's well known. The annals of science have endless documentation of it. So here's mc2.net/refraction. I have several dozen papers, empirical measurements. These are not people that are just doing math. This is people that have gone out in the field. They have measured the effects of refraction. Some of these papers compare the effects of refraction to the theoretical things that should happen. And then some of them do both. Some measure it, Some predict it, some do both. In particular, though, I want to bring your attention to this one where they did both, called Results of Leveling Refraction Tests by the National Geodetic Survey. This, they used invar rods, and they measured the vertical temperature gradient, and they measured the amount of elevation change based on that. So it's a nice one that tests hypothesis with observation to see how closely they match, and it's a very good close match. So now, Chad, where did you get that equation 1.22 times the observer's height in feet?
Where'd I get the equation?
Yeah.
Well, I mean, it's online. It's a formula for the geographic horizon. It's 1.22 times the square root of the observer's height.
Yeah, I'm just asking where you got it, because
online.
I'm asking because I'm wondering, are you a parrot, or are you a free-thinking, independent researcher that went and looked it up yourself and verified it?
Well, I seen this referenced in multiple places.
But you don't know where you found it.
No, I don't have.
Do you remember the name? Do you remember the name that I mentioned earlier?
Quantum eraser?
Yes.
Yeah.
So quantum eraser is where that number came from. He's the one that introduced that number into the flat Earth conversation. Here's him talking about where he got it from.
The subject matter expert, Andrew Thomas Young, our favorite guy.
You hear that?
Yeah.
That was quantum eraser speaking about Andrew Thomas Young. Andrew Thomas Young is where he got that specific formula from. Here is Andrew Thomas Young's webpage where quantum eraser got it from. This is the exact page where he got it from. And you see the highlight there, 1.23 miles times the square root of the eye height in feet. It's actually 1.225. Sometimes people round it to 1.22, sometimes 1.23, sometimes they say 1.225.
Yeah.
This
1.225, I think.
This is the provenance of that formula in this discussion, and it came through quantum eraser from Andrew Thomas Young's website. That's where it came from. But now you see right here where it says no refraction. You see that? Mm-hmm. That formula is specifically for no refraction.
Correct.
Right? Now, but you see that little headline down below, refraction considered simply.
Yes.
Right? We can go to that section. Here's that section, refraction considered simply. He goes through the other things, how to get it in the simple case, where there's a non-chaotic refraction situation, which is almost always the case, because there's basically, if you're in the air, you're always going to have some refraction. So he says here, in the simple case, 1.32 miles times the square root of the height in feet. Right? But now, you see at the bottom there it says variable gradients?
Yep.
Here's the variable gradients, right? And he goes through variable gradients. The problem is, of course, without having very precise measurements, you can't make very precise predictions about what you should see on the globe, right? And then that last one there says nasty complications. So here's the nasty complications part. And of course, it goes into more detail. There's all sorts of things that can happen, like ducting, where you have layers, where between the layers you have the index of refraction gradient is so steep that Snell's law says that you're going to get total internal reflection. That's the mirroring that you see above the road. That's total internal reflection is what it's called. And so you can get ducting where that's happening top and bottom, and it's bouncing in and out of this duct. That happens. It's documented. So at the end here, he says, but occasionally they will be wildly off, particularly if superior mirages are visible. So that's about visibility in the distance to the horizon. So if you use 1.23 or 1.22 times the eye height in feet, you are using the no refraction version. And so that would be a great instance for where you have no refraction, which doesn't ever happen. Never is there no refraction in the air. If it's refraction considered simply, a non-complicated situation, then the 1.32 might be a better number. And in fact, this number goes back to Gauss, the guy you brought up earlier.
Yeah. Mhm.
He did a bunch of measurements of refraction in air, and the number that's being used here dates back to Gauss. All right. Anyway, variable gradients, nasty complications. So here is in the same video that you're talking about, that you got it from. This is the normal case. This is what you see most of the time. You see the bottom of that, the left rig there is obstructed by the horizon, and the right rig there is right near the edge. There's a little bit blocked because underneath the catwalk is a little more space, but that doesn't matter. We're looking at the one on the left. This is the case where you might say, I would probably say refraction considered simply. And then in the video, this is right from the video, once in a while, not very often, there will be days when conditions are right to see the full image. So he found the corner case, the outlier, and this is what he got, right? This is the one where you said you said the horizon is behind that second one. But when I look at this, I do not see no refraction. I do not see refraction considered simply. I do not see variable. I see nasty complications here. That's what I see. The audience is welcome to make their own conclusions about what they see here. But if you don't have a very precise measurement of the index of refraction between the observer and the object there, you cannot make a precise determination of what you should see. You cannot make a prediction. But remember, he said, some days we see the full image, right? Do we see the full image here of the left platform? Chad, do you think we see the full image?
I mean, there's definitely not the full image there.
Well, here's a picture from Getty Images of that very same platform.
Yeah, it's compressed at the bottom.
So you don't see the full image.
Isn't that what I said?
Yeah. So my point is, this is a lie.
I mean, it's the full image with refraction.
With nasty complications, I think.
Well, I mean, listen, refraction is not categorized as nasty complications. I'm not going to use some gentleman as a source. Refraction is very complex.
Absolutely.
Very complex.
Yeah,
and
very complex.
And I can show you many examples of the horizon coming closer from refraction.
Right.
I'm wondering if you can show me any examples of the horizon getting further away.
Yeah, right here, we're looking at it. So,
yeah, but you said we don't know the exact index.
No, we don't know the index, but
we
I
don't
can
know the coefficient. We don't know what's going on here.
You didn't ask that.
Can you show a video?
Chad, you didn't ask that. You didn't ask that. You said I'll quote you as close as I can. Can you show me an example of the horizon moving farther away? And I said yes. You didn't ask.
I don't think you didn't. But that's not what this is.
So here is.
Show me two pictures. Just because there's a mirage, we get refraction even without a mirage. We don't need just because the visual of the image.
This one is refracted as well. Yeah, definitely.
We always get refraction.
That's my point. Exactly.
And the ocean will go up and down, but and you can see.
All right, let me finish my presentation, Chad.
Go ahead. I'm sorry.
All right.
You asked me a question.
Yep. You kept going, so thank you for pausing.
All right.
So we do not see the full image. Here's the full image. Here, there's a catwalk underneath. The catwalk is blocked as predicted by the globe, by the horizon. How do we know that it's a horizon? Well, because the globe predicts it, and there are nasty complications. So I will give this multiple choice to the audience here. On the left, do we see no refraction, refraction simple, variable gradients, or nasty complications? And on the right, same question, same options. Which one do you see? I look at the one on the right and I see that crane being straight. I look at the one on the left and I don't think the crane is actually shaped like that in reality. It looks to me like nasty complications. That particular image on the left, I cannot make any predictions about because there is no data about the temperature between the observer and the platform. So you can't, if you draw any conclusions from it, you are digging some desperate holes there, is what I say. All right, that's the end of my presentation.
Juan, did you have any follow-up questions, or do you want me just to go right into the kind of the rebuttal?
So I would kind of, I know you both presented the platforms. Now, my question with the platforms is, are the platforms supposed to be proving like the distance between them and everything? Is it supposed to be proving that there's, for the flat Earth side, is it supposed to be proving that there's an N?
It's a
Earth,
reference. It's a reference distance. We know those platforms are a certain distance, and we know where the horizon should be, but then refraction obviously is what they're claiming takes it out. What I'm saying is there's always refraction, but the refraction brings the horizon closer, not further away.
Okay. Okay,
and I can go ahead.
Go ahead. I'm sorry.
The example we have here is when the conditions are very clearly not heavy refraction, the horizon is near. And when the conditions are very clearly lots of refraction, the horizon is moved farther away. So it's the opposite of what you've claimed.
So what happened there was a cherry picking of images. You do not have to have heavy miraging to have heavy refraction. And that's just the reality. Refraction and what we see is very complex. And it's not just when there is refraction, the image is busy. I can show you. Let me just go to my, am I sharing my screen?
You're not right now.
Okay, let me share my screen. Hold on one second.
I'm gonna be editing for hours.
All right. So let me show here. Now this, if you look, this is an image. Now watch. Refraction, it disappears. This is a lake about 600 foot long. And you see how that would look like the horizon's closer? You see the boat's cut off? Refraction is very complex. And it does not have to be like the image. I'll be honest with you, MC Toon. If I just was uneducated and I saw the image, I would say, yeah, clearly. But the reality is that's a cherry-picked image. And I can show that same image.
Quantum Eraser did cherry pick that image because as was in the video said, quote, once in a while, not very often, there will be days when conditions are right to see the full image. So that is the admission of cherry picking right there in the video.
Yeah. So let me show you this. So you mentioned refraction goes, always curves down, and obviously
not always. It's the general case. It curves to the density. The general case. And over water, it's different conditions generally than like if you're over concrete or over grass. And
I think refraction is pretty much
the citation I gave gives different measurements over different surfaces: grass, dirt, concrete, ice, water. Or away from it, like not skimming the surface. When you get more, you get less variability when you're not skimming the surface.
Yeah, so you pick any circumstance, and the refraction is going to change day to day.
Yeah.
This right here shows how actual refraction can cause, even though it bends down, it can still reflect up.
That's showing bending light up, not bending light down.
That's what I'm saying. My argument essentially is you're seeing upward refraction. That's what's bringing that horizon closer to you. That's why when we lift up,
go back to that picture. Bring that picture back up with the camel.
Yeah, right there.
All right. Do you see in the air there? What's that shiny thing in the sky?
Sun.
The sun. Right. You see that differently on a sunny day than on an overcast day. When it's sunny, the sun is heating up the ground, so the ground is hotter than the air. That's what happens on a sunny day.
What we see is upward refraction with many different conditions. That's just, there's never been a scenario where you can make a horizon go away from the observer 9 miles. You can't show me that.
I showed it. I literally showed it.
No, you didn't.
Yeah, the platform habitat, the farther one, still was behind the horizon. The bottom of it was blocked.
So does the refraction not work on the platform?
Of course it does. The refraction, the platform was heavily refracted. I can bring it up again. You can see how much refraction is on the platform.
Well, I'm saying, why didn't the platform go out 9 miles? Why didn't the platform go out 9 miles?
What do you mean? Why didn't it? Doesn't.
If the horizon went out 9 miles, why didn't the platform go out 9 miles?
That makes no sense.
I know.
That makes no sense. How would you expect the platform to move out 9 miles? What would that mean?
Well, what's the mechanism that the horizon goes out 9 miles?
Downward refraction.
Well, wouldn't that be the same?
No.
The
platform wouldn't move out. It doesn't move the platform. You'll see more or less of it, because more or less of it will be obstructed when the horizon is more or less of it blocked as well.
So this right here is refraction. This is refraction.
Yeah, all over the place. Exactly.
Yeah, you see how the buildings are coming and disappearing. That's what you're seeing when you show pictures. You can see tons of refraction here, tons of miraging, and yet the ground, the horizon is not moving out 9 miles. And again,
there's no measurements in this, so don't make.
You don't have to have a measurement to know which way it goes directionally. It either goes out or in.
But you also don't know the base case of that video.
Yeah.
Where would everything appear with zero refraction? You don't know. You can't make that claim.
Well, I mean, I am not making that claim. I'm not trying to make that claim.
Okay.
I'm going to try and stop recording here. Okay. So I mean, I think that's all I got. Do you want to come?
Yeah. My point is, if you don't have a very good measurement of the index of refraction or some mechanism, some way to quantify that, when you see things that are obviously very complicated, you cannot draw conclusions unless you have the details. If you don't have the details, you say, well, that looks crazy. At the end, let's go and find a better observation where we're not having crazy refraction, where we're not having nasty complications. That's what you must seek out. So when surveyors do their work, they seek out times when the refraction is less. So if you look at the transcontinental triangulation again, they did measurements at certain times of day, and it's documented what time of day they did those measurements. That's based on knowledge of when is a good time of day and when is a bad time of day to make measurements.
Absolutely. Yep. No, we know refraction's there. I'm just saying refraction makes you see a shorter distance. That's it. That's all I'm saying. We see more clear when it's wintertime. We see more clear. We see the stars more clear in the wintertime. Refraction actually brings things closer to you. That's all I'm saying. And I think that's pretty much
anyway,
all I got.
I'll go back for the viewers. mctoon.net/refraction has somewhere around 20 empirical measurements of the effects of refraction that you can look at. So it's not my opinion. It's not Chad's opinion. It's actual empirical measurements in the field. That's all I got.
So if neither of you have anything else, do you guys want to go in with rebuttals?
I think
share your final thoughts.
I think we shook that out.
Yeah, that's pretty much, I think we presented our case.
All right. So with that, I don't know how regularly, I'm going to be honest, I don't know how to end a debate. I have done debates, but they're regularly political. So they end themselves originally. So this is not that much of politics as much as it is, this. But I want to thank you both, for joining. MC, thank you for taking your time and joining us. And Chad, same with you.
It was a pleasure, both of you. Thanks a lot. It was an absolute pleasure. I had a lot of fun.
Here we go.
MC Toon, drop that beat.
All right. Let it flow. Let yourself go. So I know that is the tempo.
So, yeah, let's do this. So,
Let's do this. Yo, it's MC Toon, the debunking tycoon. I shatter flat earthers, make them face the moon. Your attempts are decent, but they'll swoon in the face of my logic like a deflated balloon.
Oh, MC Toon, the one soon cartoons. I'm the real say, send it first to their dues. Your theories are like old brews, sweeping ignorance or just spreading the views.
FDFE stands for fumbling the facts, evidently. I drop truth bombs so splendidly. Your approach is soft, mine's unrelenting. I bring the science while you're just venting.
MC Toon, the buffoon with silver spoon. I got the pseudoscience, make them change their tune. You're the sidekick, I'm the maroon. When it comes to debunking, I'm the brood.
In the rizzle dizzle. But hey, FDFE, we share the creed to educate and debunk, plant the seed. Though in this rap, it's clear indeed I've got the upper hand, then word indeed. Alright, hold on a second. The Zoom call died. Everything died! No!